Hello, my dear students. In this session, in session 2, I'll take vector subspace. Before I start the vector subspace, I want to recall the definition of vector space. How you define vector space? To define a vector space, we need a non-empty set containing vectors with two defined binary operations, that is vector addition and scalar multiplication, satisfy the set of laws. Set of laws means vectors, the set containing vectors under the binary operation vector addition, that means internal composition, is an abelian group, means closure law, associative law, identity law, additive inverse law, commutative law holds good. Similarly, A times of alpha plus beta is equal to A alpha plus A beta, one scalar, two vectors. The next one is alpha plus, not alpha, A plus B of alpha is equal to A alpha plus B alpha, where A and B are the scalars, alpha is a vector, here alpha and beta are the vectors, A is a scalar. And last one is A dot alpha is equal to alpha dot 1 equal to alpha. Then we call it as a vector space. Shall we start the vector subspace now? The definition says like this: a non-empty, this is very important, to define a vector space or subspace, whatever it may be, the set should be non-empty. A non-empty subset W of a vector space V is said to be a subspace of V if W, non-empty subset W with defined operations, that is vector addition and scalar multiplication, must satisfy the laws of vector space. Let me repeat. A non-empty subset W of a vector space V is said to be a vector space of V if W itself a vector space under the same binary operations, that is vector addition and scalar multiplication. There are two types of vector subspace, namely improper and proper. The set containing additive identity and the vector itself are called improper. That means only two are improper, the rest one are proper. Now the important result, that is necessary and sufficient condition theorem for a subspace. A non-empty subset W, a non-empty set W, just a minute. A non-empty subset W of a vector space V is said to be a vector subspace if and only if it satisfies two conditions, that is vector addition condition and scalar multiplication. If I combine these two, vector addition as well as scalar multiplication, we can form a beautiful mathematical representation, that is A alpha plus B beta belongs to W. This is the combination of vector addition as well as scalar multiplication, where A and B are scalars, alpha and beta are the vectors, belongs to W here. Let me prove this beautiful theorem. If W is a subspace, then we have to show that this condition is satisfied. Okay. If it is a subspace, 100% it is a vector space. If it is a vector space, it must satisfy all the laws of vector space. Abelian group under addition, distributive law and the last one, 1 dot alpha equal to alpha dot 1 equal to alpha 1. Let me see. Alpha is a scalar. Sorry. A is a scalar. I'm sorry for that. A is a scalar. Alpha is a vector. Then their product A alpha belongs to W. I mean, if A belongs to F, alpha belongs to W, then A alpha belongs to W. Similarly, B belongs to F, B belongs to W, then scalar multiple of vector, that is B beta belongs to W. If I add these two, I mean summing these two, what we get? A alpha plus B beta belongs to W, the standard result. That means what we proved here, we proved if it is a subspace, then it will satisfy both the condition, that is vector addition as well as scalar multiplication. The combination of these two, I mean vector addition and scalar multiplication, we can form this step result, that is A alpha plus B beta belongs to W. Conversely, since we have if and only if, therefore we have to take converse part also. If W is a subset of V, satisfying A alpha plus B beta belongs to W, where A and B are the scalars, alpha and beta are the members of W. To show it is a subspace, it is enough. We have to show that it is a vector space. If I take A and B as 1, closure law holds good. If I take A as minus 1, if I take A as minus 1, B as 0, we get minus alpha belongs to W. That means if alpha belongs to W, then the additive inverse is also belongs to W. Fantastic. This shows that the inverse element exists in W. If both are 0, that means if both the scalar take 0, then we get 0 vector belongs to W. This shows that 0 vector is also member of W. Clearly, since the closure law holds good, 100% the associative law holds good, as well as the commutative law holds good. This shows that what it shows? This shows that a non-empty subset W of V under addition is an abelian group. If beta is a 0 vector, we get A alpha belongs to W. That means what it shows, W is closed under scalar multiplication. Since vector addition law holds good, scalar multiplication also holds good, therefore all the laws of vector space holds good. It indicates W is a subspace of V. If I say only this much, I mean W is a subspace of V is not complete. We have to make it complete only when we define over particular field. Therefore, we should write always W is a subspace of V over a field F. Okay. Now, two important properties of subspace. One with respect to intersection, the next one with respect to union. Okay. Let me take the intersection of two subspace first. If W1, W2 are the two subspace, 100% their intersection is non-empty because the additive identity element 0 exists in this set, that is W1 intersection W2. Let me prove this result. If alpha and beta are the members of W1 intersection W2, using set theory result, we write this one as alpha beta belongs to W1 and alpha beta belongs to W2. Let me take separately. Alpha belongs to W1, A is a scalar, then their product belongs to W1. Beta belongs to W1, B belongs to F, that means B is a scalar, then their product belongs to W1, that is scalar multiple of a vector. If I combine these two, I mean summing, what we get, A alpha plus B beta belongs to W1. Similarly, we can show A alpha plus B beta belongs to W. A alpha plus B beta belongs to W1. A alpha plus B beta belongs to W2. What it shows? It shows that A alpha plus B beta belongs to W1 and W, intersection of W1 and W2, where W1 and W2 are the subspace of vector space over a field F. This completes the proof of what? Intersection of two subspace. Now I will take the union of two subspace. Sometimes we have to prove the result by taking an example. Let me take a field containing real numbers, or be a field containing real numbers. W1 is a subspace and it is ordered triple. Strictly, just a minute. R is a field of real numbers. W1 is a subspace containing ordered triple. The condition is two elements are strictly 0 and one is non-zero. W2 is another subspace. Here also strictly two elements are 0 and one element is non-zero. Okay, in both the subspace two elements are 0 and the next one is one element is strictly non-zero. Since it is ordered triple, A is non-zero, remaining two elements are 0. In W2, strictly second element is non-zero, the first and last element is 0. Okay, if I add these two, what we get? If I combine these two or add these two, what we get? We get an ordered triple where first one is non-zero, second one is also non-zero, whereas the last element is 0. It is against to W1 and W2. That means it does not belongs to W1 union W2. This shows that the union of these two subspace need not be a subspace. This completes the proof of the subspace with respect to union. I mean union of two subspace. I hope you understood this. Thank you. In the next session, I will take linear combination of vectors, linear span of vectors, linearly dependent and linearly independent. Thank you once again. Have a nice day.